Hi, my name is Twisha Thora, and this is my lab 4. So the goal of this lab is to investigate the distance dependence of a magnetic field of a small bar magnet. We're going to measure the magnetic field on the magnet both on and off axis, and then simulate this using code, and then compare both of the magnetic fields to see if there's a difference. And then here are some of our findings, but we'll get into that. Here are a couple of the key concepts. I won't read through all of it, but I will just touch on Biot-Savart law, which relates the magnetic field produced by an object at an observation point to both the current through the object and the distance between the object and the observation point. And then if we want to calculate the electric field of a perpendicular dipole, we use this, as you can see on the right. And then if we're just calculating the general magnetic field, we use this on the right. I tried to make a bit of a visual model of what we're looking at. So that little circle is our magnetometer, which is in our phone, and then that is our bar magnet, showing how the arrows are going from the north to the south. So this is like a little bit of a visualization of what's going on. Our system is the magnetometer, and the surroundings are the bar magnet and essentially everything else, but we're only looking at the bar magnet, and we're treating the bar magnet as a magnetic dipole. On to our experiment and procedure, we have our bar magnet, magnetometer, meter stick, and tape, and we essentially mark where our magnetometer is within our phone, and then we measure the distance between the magnet and the magnetometer for different X components of the magnetic field, and we did 3 trials of each distance, and then we switched it and we did the perpendicular distance off of the axis. So we measured it up and down, and we recorded the Y component of the Earth's magnetic field. We applied the distance in the Y direction and moved to that new distance, measured that, and then repeated that 2 times. Luckily, didn't have to do all these computations by myself because I just plugged in our measured values into this sheet. And as you can see here, we got a relationship that as our distance between the 2 decreases, the magnetic field increases, which is what we would think happens. So this is the data for our off-axis field. Once again, we're just measuring similar stuff, but the important thing to look at here are our distances, our average distance, and then our average magnitude of the net magnetic field, because we will be looking at this later. And then these 2 equations here are basically, like, that top equation is what our line, if you go back to the previous slide, that's our relationship. We can essentially rearrange this to solve for a constant mu, and that is what I did, and I got that it was 1.475. So that was all of our experimental setup and modeling, and now we have to look at our computational models. So we switched over to Python, and what I did in this slide is I just established what our physical constants are. I created our bar magnet, and I entered in our magnetic moment, which is mu. And then I created a simple function for the magnetic field, which is just using our laws that we learned in class. In this slide, what I did is first of all, I scaled my arrows, and I determined around how much the distance would be. I was just trying to edit around and play around. At this point, I did 0.15 meters, I think. And then I just created 2 on-axis and 4 perpendicular observation locations. And that's what you can see here. The first 2 are on axis, and then the other 4 are perpendicular. Then I just drew a couple arrows to represent the magnetic field on axis, and then I repeated that in the next slide. As I said, I just remodeled this for the magnetic field perpendicular to the axis. So all I did here was average out my perpendicular distance, which the spreadsheet did for me. I calculated the observation location at around 45 degrees from the axis, and then I just modeled it. And here is our computational model. I know it's hidden, but what this code says at the end is that our magnetic field is around 9.47 to the negative 6 in the x direction, 2.831 times 10 to the negative 5 in the y direction, and 0 in the z direction. So as we established, as the distance between the magnetometer and magnet decreases, the magnetic field increases, as shown with these 2 points of data. Also, this is our magnetic dipole moment of 1.47545. Then here is the experimental value of our magnetic field, and then we compared that to the magnitude of our simulated magnetic field, and we got that there was a 59.27% difference. This could be due to many sources of error, such as nearby devices, because it's not feasible to just get rid of every device in the room. Also, inconsistent phone placement, because we can't exactly figure out where the magnetometer are. So these are some sources of error. Finally, I'll just take some time to address the what if question. So what if you haven't oriented your experiment to compensate for magnetic north? Well, the measured magnetic field will be different because there's no accounting for the magnetic north, both the x and y components, but the z component wouldn't change because we're not going up and down. And then finally, what if you were to stick two identical magnets together end to end and run it again? Well, the magnitude of the magnetic field would increase due to the combined magnetic field from two magnets, so it would be 2 times essentially.